In the previous video, we learned that the number of degrees of freedom of a robot is equal to the total number of freedoms of the rigid bodies minus the number of constraints on their motion. The constraints on motion often come from joints. The most common type of joint is the revolute joint. It places 5 constraints on the motion of a second spatial rigid body relative to the first, and therefore the second body has only 1 degree of freedom relative to the first body, given by the angle of the revolute joint. Another common joint with 1 degree of freedom is the prismatic joint, also called a linear joint. We can also have joints with more than 1 degree of freedom, like this universal joint, which has 2 degrees of freedom. The spherical joint, also called a ball and socket joint, has 3 degrees of freedom, the 2 degrees of freedom of the universal joint plus spinning about the axis. This table summarizes the previous 4 joints plus 2 other types of joints, the 1 degree of freedom helical joint and the 2 degree of freedom cylindrical joint. This table shows the number of degrees of freedom of each joint, or equivalently the number of constraints between planar and spatial bodies. Using this table of freedoms and constraints provided by joints, we can come up with a simple expression to count the degrees of freedom of most robots using our formula from chapter 2.1. Let's say the robot has n links. By historical convention, n includes ground as a link. The robot has j joints, and we define m to be the degrees of freedom of a single body, so m equals 3 for a rigid body moving in the plane, and m equals 6 for a rigid body moving in 3-dimensional space. We can write our equation in terms of these variables. n minus 1 is the number of links other than ground, and m times n minus 1 is the total number of freedoms of the bodies if they are not constrained by joints. Then we subtract off the constraints provided by the j joints. Since the number of constraints provided by joint I is equal to m minus the number of freedoms allowed by joint I, we can replace ci by m minus fi and rewrite the equation like this. Rearranging once more, we get this. And this is called Gruebler's formula, and it assumes that the constraints provided by the joints are independent. Let's apply Gruebler's formula to a few mechanisms. The first mechanism is called a serial or open chain robot because there's a single path from ground to the end of the robot. It's called a 3R robot, meaning it has 3 revolute joints. This planar robot has m equals 3, n equals 4, and j equals 3, and 1 freedom at each joint. Gruebler's formula tells us 3 times 4 minus 1 minus 3 plus 3 equals 3 degrees of freedom. The robot has 3 degrees of freedom as we expect. The next mechanism is called a 4-bar linkage, obtained by pinning the endpoint of the 3R robot to a particular location in the plane. This is called a closed chain mechanism because there's a closed loop. As before, we have m equals 3 and n equals 4, but now we have j equals to 4 joints. Gruebler's formula tells us that this mechanism has 3 times 4 minus 1 minus 4 plus 4 is equal to 1 degree of freedom. We would also predict this by the fact that pinning the endpoint of the 3R robot to a particular xy location creates 2 constraints, so we can subtract 2 from the 3 freedoms of the 3R robot to see that there is 1 degree of freedom. The next mechanism is like the 4-bar, except now it adds 1 more link and 2 more joints. Gruebler's formula would tell us that this mechanism has 0 degrees of freedom, but that's wrong. It still has 1 degree of freedom, just like the 4-bar. The reason that Gruebler's formula does not apply is that the joint constraints are not independent. Testing whether joint constraints are independent is not an easy task, and we won't pursue it further. Finally, we have a spatial closed chain mechanism called a Stewart platform. It has 6 legs connecting the bottom platform to the top platform, and each leg consists of 2 links and a universal joint, a prismatic joint, and a spherical joint. The prismatic joints are actuated, creating motion of the top platform, as you see in the video. Since each leg has 2 links, there is a total of 12 links in the legs, and adding ground in the top platform makes 14 links total. Each leg has 3 joints with 6 degrees of freedom total, for a total of 18 joints with 36 total freedoms. The mechanism moves in 3-dimensional space, making m equal to 6. Gruebler's formula tells us the Stewart platform has 6 times 14 minus 1 minus 18 plus 36 is equal to 6 degrees of freedom. The top platform can be moved with all 6 degrees of freedom of a rigid body. There are limits to the range of motion, of course, but these limits do not reduce the number of degrees of freedom. In the next video, we will explore another important property of a configuration space, its topology.